Hello and welcome to the course Basics of Experimental Design for Cognitive Psychology. I am Dr. Ark Verma from the Department of Cognitive Science at IIT Kanpur. As you know, this is the third week, and in this lecture, we will try and get into a little bit, you just scratch the surface. We will get into the mechanics or the principles behind experimental design. In the last lecture, I gave you an overview of what an experiment consists of: independent variable, dependent variable, control variables. We talked about manipulation, we talked about null results, and so on. Now, in this experiment, let's try and take a more specific approach to understand what is actually going on in an experiment. All right. Okay. So, in experiments, we are treading a very fine line between specificity and generality. When we are measuring a particular aspect of behavior, we are measuring a very specific aspect of behavior in a very specific set of conditions. We have a specific independent variable that we are manipulating, and we are measuring the effects of this manipulation on very specific aspects of the dependent variable. Let us say reaction time, let us say accuracy. Everything else is controlled for. Now, in controlling for everything else, what we have done is we have created an extremely unique situation for ourselves. We have basically, for example, if you were we can take any of the examples that we were talking about in the previous lecture. Just for continuity's sake, we can talk about red ink, green ink, memorizability or legibility. We can talk about say, for example, whether perceiving objects is lateralized to the left hemisphere or the right hemisphere. We can deal with any number of things. Whatever we are dealing with becomes very specific to that experiment, and if you if you go and read journal articles, they are actually not saying anything more than what their specific experiment says, and that is one of the reasons why they describe their experiments and the methods and the procedures in great detail, so that you can recreate the specific conditions and hence replicate this, so that if you are creating a situation that is even slightly different from the experiment that let us say person A has done, you might not be able to find those same effects. All right. Now, the thing is, generality is also important. Why is generality important? It is important in the sense that if whatever findings we are getting are basically tied to that specific experiment in that specific lab in that specific condition, then what is the use of that experiment? Because it does not tell me anything about the general behavior. It does not tell me anything about, say, for example, how participants in a different college, say, for example, I do an experiment in IIT Kanpur, a very specific perception experiment, for example, or word recognition experiment, so to speak. Let us say Hindi words or English words, whatever I use. Now, if my experiments are too specific and they cannot recreate or they cannot predict how a person in Allahabad or in Hyderabad will react to English or Hindi words that I have used in my experiments, then my experiment is not useful at all. So, generality is also important. We have to always tread this fine line between how specific we are going to get, and within that specificity, how generalizable our findings are going to be. Okay. So, this is one of the most fundamental principles in experimental design that I will stress upon in this lecture, and I hope we are able to understand it in some detail. Okay. So, I will be giving you broad examples, and I will be sort of going with the slides and explaining them in some detail as well. So, experiments tread a fine line between specificity and generality. To elaborate, while experiment designs aim for precision and control to ensure that the results whatever are obtained are usable and uniquely interpretable in principle. So, we want in principle whatever we have done is applicable to only that situation. At the same time, the idea is that the results obtained can also be generalized across situations, at least similar to the one that you have created. Okay. A fundamental rule here in experimental design is that we can make definitive claims only about the specific conditions, specific stimulus, specific participants that we have used in our experiment. Let us say if we have created a lexical decision experiment, tell me if this word is meaningful or not, typically is this a legal word or not, something like that. And if we have used only one kind of words, if we have used only high frequency content words, and I have done an experiment and I found a certain pattern in reaction times and accuracy, then my results are only going to be able to tell me how the same kind of words will perform in different situations. Maybe not even that, because if the participants are here are only males, in another experiment somebody wants to use only females, here there are only high school students, in some places there are only PhD students. So that will also become slightly difficult. So in a sense, what will happen is we will not be able to generalize our conclusions beyond the conditions in which we have performed these measurements. So this is something which is a bit of a dilemma. Now in the same vein, if we have measured the performance, I am just extending this dilemma a little bit. If we have measured the performance for only one person, then we can make detailed claims about only that person, because people are different, their backgrounds are different, their knowledges, their IQs, their mental state at a given point in time, even structurally and functionally, the brains are also not identical. I am not saying they are very different from each other, but they are not identical, and we know that. So if we measure two conditions that differ along the several dimensions, any of which might have caused or affected the change in the dependent variable, then also it will be difficult for us to draw any definitive conclusions about the causes or the influences on the differences in the conditions that in whatever is happening with the dV. So we can only confidently say anything about the specific conditions in which the experiment was performed, with the specific participants, with the specific conditions. Okay. So the more conditions we now we have a specific situation idea, the more conditions we measure and the more tightly control the variation in these situations, the more reliably, however, we will be able to predict about situations in general and about the causes and influences of behavior. Now this is an idea that I want you to sort of take some time and understand. More conditions, the more number of specific measurements we make, it empowers us to basically come up with more generalizable findings. Let us talk about this. So if that happens, then we can discuss only the exact items or the situations and individuals in our experiment, and when we want to talk about broad categories, when we want to talk about words in general, then basically we would need to measure every member of that category. For example, I was talking about high frequency words. Let's say we talk about low frequency words. Now does my experiment empower me to talk about all high frequency words? There are so many of them, there are probably an infinite number of them. In order to be able to predict and tell something broadly about how high frequency words function, given a lexical decision task of participants such and such kind in conditions so and so, do I need to measure each high frequency word to be able to say something about it? No. There are principles that allow us to generalize, and we will talk about them as we go forward. Let us take this example. Let us say that we are exploring an unknown function. Okay. There is this function f of x, and we know that this function returns an output which is mx plus b. So here the term x, f of x, in f of x represents the input to the function, and the output is represented by this term mx plus b. Okay. So there are two things, there is an input, there is an output. This is what we know. Suppose there is this unknown function which we just you can see in the figure. We have a method, and we have a method for obtaining the the result for specific input. When basically, say for example, when we put x1, we get the output y1, x2 y2. So for xi we get, say for example, yi, we get corresponding value. So we are sampling, every trial is giving us something, every trial we are sort of getting some output out out of this let us say participant or function in this case. Okay. Now we know precisely what the value of the function is going to be at that point. At x1 the value will be y1. So we know for that specific point whatever the value is going to be. To know the function's value at x2, we would actually have to go out and measure it. Say remember, here is this x1, for x2 we will actually need to go and measure it, we will need to sample, perform a trial at that, and get whatever value of the output is going to be there. Now in this trajectory of the function, if you see, if we measured all the points, say xi, we measured the entire trajectory here, we would know the exact shape of the function. We will know, okay, how does this function vary and what kind of values it returns. This is basically this idea of specificity that I was just talking about. Okay. Every trial in your experiment is giving you the value of x1, x2, x3, x4, but it is not telling you the entire shape of the function. But are there ways to do that? Let us see. So, if you measure several points near each other along a single dimension, let us say we can sample from a narrow range in the distribution of all possible values on the dimension 0. Let us say we take some dimension, imaginary dimension 0, then what will happen is that we can be reasonably certain of the of what the values at the intervening points would be. Okay. So, let us say this is x1, this is x2. If we sample from here, we sampled x1, x2, x3 and so on, we can basically have some idea of what the intervening values between x1 and x2 will be. Okay. So, linear interpolation basically that is we are calling it linear interpolation between these values would produce therefore a reliable estimate, assuming that the function is analytical and at least close to being locally linear. So, between points it is just a straight line. Let us say between x1 and x2, look at this figure, let us say between points it could be a straight line or something like that. Now, these two are the fundamental and very common assumptions in perception, and you hold for a lot of perceptual phenomena, perception as a cognitive function. So, by varying our inputs systematically along a given dimension, what is happening is that we are in a position to make a clear and reliable claim about both the measured points x1, x2, x3, x4 and so on, and the intervening points, the point between x1 and x2. Okay. Now, if we sample enough points, if we sort of go out, let us say we have 400 trials or 500 trials or 1000 trials. In psychophysics experiments, people have thousands of trials. Okay. So, if enough points are sampled, and if these enough points are sampled, if these sampling points are well chosen, then we can actually make claims about the dimension in general. Okay. Then we can basically say across the variations in let us say luminance of a stimulus, this is how the participant would respond. Let us say luminance was the dimension that we are concerned with. So, sampling is extremely important. How are we sampling our trials? Where are we taking our observations from? And this is again something that we will talk about in more detail going forward, but I am sort of sidestepping this in interest of the issue at hand. So, coming back, we see that specificity and generality can be seen on a continuum. You can basically be treading this thing that you are measuring specific points, but if you have measured enough specific points, you can make a slightly general claim. Okay. So, with enough specificity at hand, we can be quite general. To elaborate, just go in detail. In addition to gaining enough specific information to make reliable generalizations by sampling more points, we can actually gain the needed information about the nature of the function, about other sources, just as sampling that other people have performed, how have they picked up their trials and different conditions. Also, general knowledge about the type of function we are sampling, general laws or principles based upon previous theory and previous research and so on. So, all of that starts coming in. All right. However, also note that the interpolation or the generalization will involve always a degree of uncertainty. Because you have not measured that point, the interpolations or the estimations that you are carrying out will always have an element of uncertainty. All right. So, if the sample points are, let us say, very far from each other, x1 is here, x2 is here, or if x1 is here and x2 is right here, the degree of certainty that you can actually have in interpolating between x1 and x2 is actually more. Okay. It changes. If it is too far apart, then the degree of uncertainty is more. If it is too less, then degree of uncertainty is less. Okay. So, if the sample points are far apart from each other, then there is a high chance that the interpolated value might vary a lot from the true value, and the closer the sample points x1 and x2 are, the more reliable these interpolated values will be. Now, one drawback of sampling from very close together is that you ignore the larger picture. You do not know overall what kind of values the function will take in its outside the sampled region, outside from where you are picking up your trials from. So, there is always going to be this very fundamental trade off between specificity and generality in experiment design, and this is something that we really need to understand as the basic principle in experimental design. Now, I will set up a modeling approach that is basically followed by Cunningham and Waldreven in their 2012 book, which we are following for this course. And I'll just set up the broad parameters of this model, and then we'll take different characteristics, different things that we will study about experiments from this kind of modeling approach. Okay. So let's say a researcher wants to measure pointing accuracy. Okay. So there is a target, you go and point at it, and you're basically interested in knowing how accurately people do that. All right. So he or she can start with a very simple target, let's say a bullseye for that matter. Somewhere on the wall a bullseye is hung, and you tell the participant to go and touch this target. Now, how much accuracy, how how correct that person will be can be your measure. So the participant goes and touches the bullseye. The distance between the center of the target, the exact accurate position, and the point where the participant did touch with his or her hand will be this measure that you want to take, will be the dependent variable. This is the dependent variable, and the distance between the exact place where your participant has touched and the exact center will be the the measure will be the dependent variable. If this distance is 0, then the participant has absolute accuracy, perfect performance. If this is too far off from the center, then you have a value which will give you the disparity, which will give you the offset. So offset is your dependent variable. Now, if let us say x is a vector representing a complete description of the specific situation. Now, again remember, we are talking about specificity versus generality. The specific situation in which you asked your participant to come and touch this target. So, if x be the vector that represents this specific situation, which includes almost everything that you can think of, it could include that there is a high contrast target or a low contrast target, is 1 participant or 10 participants, the participant responded with his or her left hand, there was one trial, participant was paid for his time and so on. So, all of that is figured is condensed under this variable x. Okay. So, m of x of that specific trial is the measured response for a given situation. So, for this situation where you ask your participant to touch the target, m of x is that particular measured response. Another thing of interest for experimenters specifically, because you are targeting specific processes, is B, and B can be defined as the internal processes that we are actually interested in. Why did we want the person to come and touch this thing? Because we wanted to know what are the processes that go on in the brain that allow us to do this, perform this particular activity. All right. So, since we cannot directly measure in the brain what is happening, we will find out we cannot measure the mental representations of the distance between the hand and the bullseye and other important things that are critical to this thing. So, we cannot, since we cannot measure it, we can basically have two parts. We can basically say that this inner mental representations that are governing this measurement m is basically this variable b. Okay. It represents things like internal motor planning, estimation of distance and so on. So, B will represent the entire chain of internal events, from converting the signal when you see this perception, transduction of that thing, looking at something, transduction of that, to actual execution, pointing, that touching behavior. This chain of actions that we are actually interested in is referred to as the perception action loop. All right. Now, note that there are two parts in this perception action loop. There is perception and there is action. What is perception? Perception is basically all the processes that were involved in extracting and representing the stimuli from, and from the action side we have all the processes that are involved in planning, preparing for and executing this motor behavior of touching that bull's eye. Now, what do we have here? What are we studying through this one trial? M of x is basically B of x, whatever mental processes happened, whatever cognitive processes took place, plus an error component. Okay, because again we are not ideal executors of behavior. There is always some degree of error or variation that will always be. Okay. So, this error term basically means that the action that the participant is producing is not exactly what he meant to perform. He probably was going for the exact center of the bullseye, but he just landed, let us say, 1 mm next to it. Why did he end up at 1 mm next to it? Okay. So, there is this error component. Now, error component is something extremely important here for us to consider, because that's basically something that happens a lot with our experiments, and we should know about this to be able to interpret it. So, let us say it could be coming through various reasons. One of the reasons could be how our retina is structured. So, the human retina has a finite resolution in space and time. So, there is a degree of approximation when the stimulus is converted into these synapses, electrochemical signals, and there could be therefore an error in locating the target. So, basically your brain could not locate the target to its actual coordinate values in space. It located it with a 1 mm error, and hence the hence basically this 1 mm error in measurement happened. So, there is also what is called physiological noise. There is also a lot of random background noise going on in the brain with neurons firing and all. So, there is this random background firing of neurons that also happens, and that also may contribute to this error term. Now, this inaccuracy of the human system also represents, interestingly, a critical but often forgotten aspect of human performance. What is that? I am sure students will know we cannot produce exactly the same action twice. If you say, for example, if I have my hand here and I want to touch the exact same point every time I move from this point to that point, if you really measure, say if there was a color on this one and there was this white paper here, every time it will be slightly different, maybe an mm, maybe a smaller difference will always be there. Okay. So, that is always is going to be there, and it is sort of, if you really want to touch that exact same spot, then you will have to make a strategy and go extremely slowly and ensure that I am touching the exact same spot. Alright. So, this natural variance in how we perform basically lies at the core of our ability to learn new and unexpected things, as well as the ability to adapt existing perception action loops for a changing environment. Now, this is again, remember, it is very important in the larger scheme of things of understanding how people respond in a given experiment, and unless we understand it, designing great experiments, specific experiments becomes a bit of an issue. So, irrespective of the source of wherever where the error term is coming from, it should be clear that there is inherent unintended variation in human behavior. In other words, actual behavior we measure is not solely a function of the desired perception action loop, what the participant wanted to do or what you instructed him or her to do, but it is also a function of some inherent noise. Okay? And this therefore needs to be interpreted in our represented in our equation, and that is where this error term basically comes in. That is why we have this error term. Alright. So, we have m of x, the measurement, b of x, the internal processes, what the person wanted to do, and this error term. Okay. So, and this is therefore extremely critical in understanding humans and for understanding experimental design. We will talk about this. If error were always the same, if this error thing were a constant, let us say if it is always going to be the same, and we know that every time you make somebody do this, there will be an error term of, let us say 5%, if something it is like that. Okay, that would always produce a constant offset from the true value of b of x, the Mendel phenomena we are talking about, and it would mean that we would be able to exactly produce the same behavior every time. And by measure this by extension, the same measured behavior would emerge every time, obviously with that allowance for that offset that we are talking about. Okay. This would mean that a single measurement will always be sufficient to determine b of x. A single measure value of m of x will be sufficient to determine b of x, but that is not the case. We know that this inherent unintended variation is actually all over the place sometimes. So, if now, because it is different, if this variance in the error term is small or is insignificant, then any individual random sample of the function m x of I, for example, will be close to b x of I, then also it is not a problem. It is a slight variation and we can sort of handle with this. So, any given measurement will not really try to reflect the underlying perception action loop, but will still be very close to it. Okay. If on the other hand, this error term is known to be large or significant, then any single measurement will diverge very strongly from the actual value of b of x. basically whatever internal process that are going on. As the value of the error term is not constant and will vary from trial to trial, this is what we know about human behavior, and that we never know a priori what amount of error term will be there, we have to find a way to estimate it. Okay. What are we doing experiments for? We are doing experiments to measure specific behavior, and in that specific behavior, if there is this error term, we have to find a way to estimate it, so that we can factor it in our calculations. So, as the equation has two unknowns now, b of x and the error term, a single measurement will not be sufficient. It will not tell us exactly what we were looking for. Say for example, I do a lot of lexical decision experiments. I want to understand how does a person respond to a high frequency word, say I don't know, 10,000 times per million, frequency of 10,000 per million, and so on. I take so many words, I measure, I give a person this, and it comes of and the person gives me a reaction time of 500 milliseconds. Now, is that value of 500 millisecond definitive, and it tells me everything about that there is to know about this decision? No, I have to take multiple measurements, so that eventually I get close to how this what the original or approximate true value of this measure will be. Okay. So, a single trial of a single condition can actually only tell us what the behavior is in a very specific situation, but not why. It will not be able to tell us why it is that way, or even how close the repetitions will be to that value. So, we will not know if we just take a single trial. So, let's see what do we need. We basically then need repeated measures. We basically need a large number of measurements, so that we can approximate this b of x that we are talking about. Okay. I am stopping here. I will continue this in the next lecture, so that we can start from the same point, and we will see what are the principles of experimental design from this perspective, from being able to isolate the right m of x to estimate the correct internal representations or internal cognitive functions that are going on with individuals. Thank you.